Greetings, scholars. I hope you're well. Today we'll be covering chapter 12 of the text, which is the introduction to the analysis of variance. So what we'll do, we'll talk about when we use the analysis of variance, the expansion kind of from the t-test. We'll start with just an introduction. So we'll talk about kind of the logic behind it. We'll talk about why we use hypothesis testing with analysis of variance. And then part 2 of our lecture, we will talk about how to compute the one-way analysis of variance, the F statistic or the F test. We'll also talk about some what we call post hoc tests to determine where the significant differences lie among the main differences. Okay, so we'll talk about several things in this first part to this lecture, but this is just an introduction to give you the gist of what we'll be doing for chapter 12. Okay, I'll share my screen and then we'll get started. All right. So again, welcome back. This chapter is covering introduction to analysis of variance, or what we call ANOVA. So what we'll talk about is when we use this particular statistic of analysis, and then in part 2, again, like I said before, we will talk about how we compute it, and then we'll work on some of the other things as far as the effect size, post hoc tests, and the other things that are associated with ANOVAs. Okay. So again, as we talk about the analysis of variance, here are some learning outcomes for us. So we're going to explain the purpose of, again, the logic of analysis of variance. You'll actually perform an analysis of variance on the data from a single factor study, and that will be done on part 2 of our lecture. And then all the rest of these things are done after the study. After we do our analysis of variance, perform the analysis of variance, then you'll need to know when and why to use your post hoc test. You'll also need to, again, those post hoc tests being your Tukey's, HSD, your Shepard's post hoc tests. And then the last thing, as with all of our research studies, especially when we're talking about inferential statistics, you have to determine what your effect size is, and that will be, in the case of a one-way ANOVA, that will be an eta squared. And so we'll talk about how we calculate those values as well. Okay. Again, just like with all of our topics of discussion, all of them build on one another. So you'll need to know sums of squares, sample variance, degrees of freedom, and you'll also need, again, what is the logic behind hypothesis testing and the independent measures T statistic, because again, this is an expansion of that T statistic test. Okay, so we'll talk about why that's the case. All right. So what is analysis of variance? Again, analysis of variance is also called an ANOVA, a one-way ANOVA. So in this class, we'll talk about and introduce the ANOVA. But again, we're still looking at differences, significant differences between groups, okay, independent groups. And so we use the analysis of variance to evaluate these mean differences between 2 or more treatments. With independent measures t-test, we had 2 independent groups, but it was only looking at the differences between those 2 groups. With the analysis of variance, what that allows us to do is look at the differences of more than 2 groups, 4, 3, 4, or 5 groups, to see if there's any significant differences between those 3 separate independent groups. Okay. So what we're going to do, as always, we're going to use sample data to draw a conclusion about the general population. Okay. So just like we did for the t-test, specifically the independent t-test, we're going to do the same for the analysis of variance. So for example, you might want to know if the 3 different studying techniques lead to different mean exam scores, right? So one of those techniques, maybe I asked you all to read a passage, okay? And I'm looking at reading comprehension and how you're gonna score on a test on the information that was presented to you. So one of the studying techniques may be you read the passage, And in order to study for the exam, you're just going to reread the passage. Okay, so that's the one studying technique. The second studying technique is at the end of the passage, you have questions that you're going to answer based on what you read. Okay, as a studying method for preparing for the exam. That's the second method. The third technique will be you read the passage, and then you have to develop and then answer the questions that you develop on your own. Okay. And so those are three separate techniques that you study. I want to measure your exam scores as a dependent variable. And again, those in three independent, the independent variable is going to be those three studying techniques. And then I want to see if those independent variables, those different levels, if there are statistically significant differences in those exam scores to see which of those techniques provides the highest success, right? The highest performance for studying, okay? Research has shown that when you read a passage and you create your own questions and answer your own questions, that usually leads to better retention of material. So just food for thought as you study for the exams coming up next week, right? Preparing your own research questions, your own flashcards, that oftentimes helps you to retain and learn the information. Okay. So again, here's just our visual representation of what we talk about. Okay. So if I had those three separate studying techniques, you have sample 1, sample 2, sample 3. Those samples are drawn from three separate populations, independent populations. And each of those has their own sample size. In this particular case, we have three groups with all of the same sample size, and each of them has very different mean scores, right? And so what we want to do is we want to determine if those mean scores are any different or statistically significant from one another. You also have your sums of squares, and when you have your SS, say for instance, population 1, sample 1 has an SS of 114, you're going to use that sums of squares to then calculate your variance. Your variance then also calculates your standard deviation, and that variance would allow you to get an idea of what the amount of the spread within the each treatment, right? So you're looking at each of those variances for each independent group, okay? So with analysis of variance, you have what we call a factor. And the factor is that independent variable, and it designates the number of groups or the groups that are being compared. So in the example that I used before, I use those three studying techniques, right? So the studying techniques, that is the factor, right? That is that one independent variable, and that independent variable is broken up into three different levels, okay? Three different levels or three different individual conditions. So when we say the levels of a factor, those are the three factors, those three levels, okay? So you have, again, just rereading the information after you read it. You have answering questions that are pre-prepared for you after you read the text. And then you have your creating your own questions and answering those questions after you read it. And those are the three levels. With the analysis of variance, again, some other terminology that you should be familiar with is factorial design. So this is a study that combines two or more factors at once, right? So instead of it being just those three independent factors, those three studying techniques, maybe I also want to incorporate male versus female. How does the performance vary for male versus female? So I'm adding a layer of factor, another factor, right? So instead of having one independent variable, now I have two independent variables. One independent variable has three factors, right? Those three techniques. And then the second independent variable has two factors, right? Or two levels, right? Male, female, right? So again, that would become a factorial design. That would be a 3x2. And so you have 6 individual scores, 6 individual conditions, okay? All right, so when we talk about the hypothesis test, we're talking about, again, that null hypothesis. When you talk about hypothesis test, you have to state your hypotheses. That's the number one step, right? So when you state your hypotheses, the null hypothesis is just saying that the treatment conditions have no effect on the participant scores. That means on average, there is not much difference at all between the three separate treatment conditions, right? So in the population, there's an equivalency between or among all three populations. And again, there is usually never a perfect equal equivalence between those two population means, but it only means that there is not enough evidence to say that they are significantly different from one another. Okay, so that is the null hypothesis, right? When you talk about the alternative hypothesis does not say that all of them are statistically significant from one another, right? They just say that there is a significant difference among at least one of the mean differences, right? So you have three populations. Population one and population two may not be statistically significant, excuse me, but two and three might be, right? And then one and three may be statistically significant, but we have to figure out where that statistical significance is, right? So again, we're just saying that there's at least one mean difference among the populations that is different, one mean difference that is significant, right? The issue with this, though, is again, when you are looking at the null hypothesis, right? How many ways can the null hypothesis be wrong, right? Because all of the means are different from every other mean, right? How do you determine if one of the means is different from mean one, is different from mean two, or is mean one different or significantly different from mean three? That's when the post hoc test that we'll talk about in part two of this lecture, that's when those come into play, right? So again, some of the means are not different from other means, right? But other means do differ from some of the means. So when you do your alternative hypotheses, right? All you're saying is population one is not equal to population two, which is not equal to population three. Again, all three means are different, right? And so that is the alternative hypothesis, right? But you also could, specify, if you want to do a hypothesis very specific, you could specify that one of the means are the same and that the others are different. But for the purposes of our research and for this class, the indication would be, let me point this out, highlighter or laser pointer. So we're looking at, again, H1, right? We're looking at population one, it's not equal to population two, it's not equal to population three. That's what we use for our alternative analysis for the purposes of this class, okay? So again, why are we using the ANOVA, right? One of the reasons why we use it is because we want to compare more than two groups, right? That's the major reason. The t-test can compare two means, right? So what we could do, if we wanted to, we have three populations or three samples, we could do what, three comparisons, right? Population one to population two, population one to population three, and then population two to population three, right? Those three mean comparisons. But what happens with that? Each time you do a mean comparison, there is a chance that you will have a type 1 error, right? That means you reject the null hypothesis when the null hypothesis is false, right? So it's a false positive. And we don't want that. We don't want a false positive. We want to reject it if the null hypothesis is in fact true, right? So what we do is the one-way ANOVA is just using one test, right? It's using one test, simultaneously looking at the differences, and that one test eliminates the error that is accumulated by doing the three individual t-tests, right? Because as you do more and more t-tests, you have a cumulative probability of a type 1 error. So if I set my significance level at 5%, right, that means simplistically, I add those 5% significance levels up because that is my percentage or my probability that I'm going to get a type 1 error. I add all of those three up, right? So I got 5 plus 5 plus 5. That's 15% likelihood that I'm going to get a type 1 error, right? Simplistically, right? But imagine if I just did all those ANOVAs at the same time, right? And I did the ANOVA at the same time, all of the mean differences simultaneously, I reduced that level, right? So when we talk about each test has its own type 1 error, that is what we consider a test-wise alpha, right? And so that's that 5% that we talked about, because the significance level serves as that significance level, or that probability that I'm going to type 1 error, right? The cumulative property for type 1 error for t-test accumulates, right? Test-wise alpha turns into experiment-wise alpha, right? So experiment-wise alpha is that cumulative probability. The test-wise alpha is that one test, right? So your experiment-wise and cumulative, as you add all those alphas up, that's going to be better than the test-wise alpha. And so what I want to do is I want to reduce that amount of probability that I'm going to get a type 1 error, because that type 1 error is not good, right? If I say that there is an effect when there in fact is no effect at all, that means my research is not accurate. I don't want that. Okay. So again, with an ANOVA, we use it because we want to eliminate the likelihood of getting a type 1 error, and by again evaluating all the mean differences at the same time with one test, regardless of the number of means, right? We avoid the problem of inflated experiment-wise alpha, which then protects us from committing a type 1 error. So then what else happens, right? So, it's not possible to compute a sample mean difference between more than two samples, right? So what happens is we have to find an F ratio that is going to indicate what value is significant enough, right, for us to reject the null hypothesis and say that there are some mean differences among or between or among the mean differences in group, right? So if there are only two samples and I have means of 20 and 30, that's only a 10-point difference, right? What if you had a third sample with a mean of 35, right? So instead of just looking at mean differences, right, because we can't compare all these mean differences at the same time, what we'll do is we use variance. Variance is an indication of the differences between the groups, right? So the higher my variance, that means the groups are a lot more different, right? The lower the variance, right? So if I had a variance, say specifically if my first mean was 20, my second mean was 21, and my third mean was 22, that's a very, very little variance between or among those three means, right? But in this case, right, we got 20, 30, and 35. That increases the variance a lot more, which increases the likelihood that I may get a significant mean difference, right? So we use the variance to define and measure the size of the differences among those sample means, instead of just using the two means, right? When we have those two means in a t-test, it's very, very easy to do because you can look at the point differential. But when you have more than two groups, you have to use the variance, and that's what we'll be using. And that's what they call an analysis of variance. So we're analyzing the differences among those sample means to see if there are any difference or not. Okay. The F ratio that I just mentioned, and we'll talk about the components of the F ratio, but it's based on variance instead of a sample, right? It's based on the variance instead of a sample, and we have to be mindful of that as we move forward. Okay. So let me share. I don't know why I stopped sharing. Okay, so when we talk about variance, right, a variance is again a measure of difference, and so that's why we use variance. The F ratio is based on variance instead of sample mean differences. So we're looking at the variance between our sample means, and then we're also looking at the variance within each of our groups, at somewhat of a within group variance, right? And so we'll talk about those different components. So again, variance, use it to define and measure the size of differences among sample means. That will be considered our numerator as we talk about it. So I will move a little further so you get an idea. Okay. So here's just an example. Here's an example of what we have for the first set. Okay, for the first set, this is variance among sample means. As you can see, right, for the example that we just mentioned in set one, you have a mean of mean 1 is 20, mean 2 is 30, and then mean 3 is 35, right? And then also look at the variance for set 1. Okay, so you're looking at the variance here. Okay, the variance is 58.33. Okay, let's take set two. Set two, you have a mean one of 20, 28, 30, and then 31 respectively, with a variance of 2.33. So as you can see, the differences between set one, the differences between the means in set one and the means in set two are very, very different, right? So the variances indicate, right, 58.33 versus 2.33. The higher your variance, the bigger the differences are between or among those sample means. Okay, so these are a lot closer together. You got a 2-point difference here, you have a 1-point difference here, and then from 28 to 31, that's a 3-point difference. Again, very, very different. The likelihood that you're going to get a significant difference among any of those values, very, very low. Okay, so when we see set one, the likelihood increases because that variance indicates the level of differences between those groups. Okay. So when we talk about the test statistic, right, we're talking about an F test. Okay. The F ratio, again, gives me the variance, the denominator, which measures the mean differences that would be expected, right, if there is no treatment whatsoever, right? So this is the variance that is expected with no treatment effect whatsoever, okay? You also have a variance that again exists between the sample means. So I'm going to go back one slide, and I want you to see what I'm referring to, okay? Okay, so when I go back here, okay, within each sample mean, okay, each sample mean does not, they experience the same treatment. Okay, each sample mean, so mean one, everybody in the sample and mean sample one receive the same treatment, right? So there is no treatment effect associated with those in group one. Group two, the same thing. They all experience the same treatment effect, right? Everybody in that same group experienced the same thing. And the same thing with group three. Everybody in group three experienced the same thing. The only difference between the members or the participants in each of these groups are their individual and unique differences among them, right? And that's why you have these differences within the group, right? But within each group, each person, each participant experienced the same treatment, right? So with that being said, that means that there is no treatment effect within these variances, right? Within these variances, there is no treatment effect whatsoever. But between them, that's when you see this treatment effect because each sample should be different based on the treatment. If the treatment make any effect or play any significant role in the differences between those scores. And that's what we want to see. Okay. But again, for the F ratio, again, you have the variance. This is between samples. So this is going to be the variance between mean one, mean two, mean three. And then the variance, the difference is expected with no treatment effect. These are going to be this is going to be the variance that is within each group. And we'll explain a little further what that means. But we're looking at the variance between each group, and then we're going to sum all of those variances up to determine what that within group variance is for the entire sample or the entire group of samples. Okay. So here's another example that we look at, right? So within each group of the sample, right, we have a mean of 4 for sample 1. We have a mean of 2, a mean of 1, and a mean of 1 for sample 2 and sample 3. As you can look within the groups, you see that there's some differences within each of those scores. So you got 4, 3, 6, 3, 4, and you get an average score of 4, right? So, but within each of these treatments, each treatment has the same exact treatment, right? These people in these groups, they experience the same treatment, right? The people in these groups, they experience their own individual treatment. And then treatment 3, they experience their own individual treatment, right? And each of these treatments is very different, right? So these persons received the same treatment, they did, and then here they did as well. Notice that there are differences among or between the persons in each of the groups. And when we talk about these differences, this is just individual differences, right? Each person in each group is going to score differently based on just them being individuals. And so that's what kind of makes up the differences between each person in the group. Okay. All right. So when we talk about the analysis of variance, this is the logic behind it. Okay. Because we talked about the differences between groups, right? Between each sample. We also talked about the differences within groups, right? So when we talk about analysis of variance, this analysis means that we're dividing, right, the entirety of our variance into smaller parts, specifically two parts, okay? 2 parts. So the first step is to determine the total variability for the entire data set, right? So we're looking at if each sample had a group, each sample had a sample size of 10, and I had 3 samples, that'll be 30 participants, right? So the first step is to determine the total variability for the entirety of that sample, right? And that big sample, the grand mean of that, and that's going to be those 30 people. So I'm looking at the variance among all those 30 individuals, right? Once I get that, then I can divide the total variance into 2 basic components. The first component is the between treatments variance, right? And that variance is, again, considered where we're looking at the difference between mean 1, mean 2, and mean 3. We're looking at the variance between those three numbers, right? So this variability results from those general differences between the treatment conditions, right? And the variance between the treatments measures the difference between those sample means. That's what's going on. I want to know what that variance is. And just like we saw, let me go back. So this value here, that's some variance there, right? That's the variance that I get between my samples. You're also going to get some variance here for mean 1. You get some variance for mean 2. You get some variance for mean 3. And again, this is my variance for all of those groups, right? This is the variance for all those groups. And we see larger variance here versus smaller variance here. Okay. The second component, number 2, is the within treatment variance. Okay. So we're looking at the variability within each sample. And as I go back, so this is the variability within each sample, right? So we're going to calculate the variability within treatment 1. We're going to also calculate the variability in treatment 2 and the variability in treatment 3. And this one may have a higher variability or variance than these 2 groups because they are very, very similar in their scores. Okay. So again, 2 components. The first thing you're going to do, you're going to get the total variability. This is the variability or variance for the entire data set. Then you're going to divide that variability into 2 components. The between treatments variance, which incorporates the differences between the treatment conditions or the sample means. And then you're also looking at the within treatment variance, which is looking at the variability within each sample. And what you're going to do is you're going to aggregate those within group variance, within or among all 3 of those groups. Okay? So again, you got your total variability, okay? And with the total variability, these are my 2 components. You got the between treatment variance, and you got the within treatment variance. Within treatment variance and between treatment variance have 2 components that make up that variance, okay? So for the between treatment variance, there are 2 things that will explain the variance between those sample means. And one of those things is going to be the systematic treatment effects, right? And the systematic treatment effects is referring to whatever that independent variable is, right? So say we're talking about those study strategies. We got 3 study strategies. I got one where you're just rereading the passage, one where you're just answering pre-ordered questions, and then the third one is where you're creating your own questions and then answering those questions, right? The variance, right? The systematic treatment is, again, splitting those 3 treatment groups into those 3 groups, right? So we're going to see some differences among exam scores just based on splitting them into those 3 groups. And that is what we call the systematic treatment effects, okay? The random unsystematic factors That is the variance. Again, like we talked about, that's just the individual differences. And the individual differences, I mean, that we're all individuals, we're all different. And so with that, we we don't have and we won't have all the same scores, right? If we all took the same spelling test, we're not all going to get the same scores because we're each individual and our vocabulary is different, right? We all don't spell the same. If we were to take a math test, right, that math test is going to vary based on each individual person, just simply based on individual differences. Each of us has different math skills and different efficiencies in math. Okay, so again, those are the two components of between treatment variance. Okay, within treatment variance, it only has that one factor, right? Is that random unsystematic factor, right? And that is, again, those individual differences. That's just random. So um, within each sample, we aggregate all those variances together, and that is considered our random unsystematic factor. But again, this will be considered my numerator from our F ratio. This is my denominator, right? And so with it being a ratio, these values, the lowest that you can get, okay, the lowest that you can get would be 1, okay? Anything above 1 is good, okay? And we'll talk about the values for the F ratio, okay? So when we talk about the random and the unsystematic error, there are 3 things that can come from those sources, right? So again, the variability for random and unsystematic variability, again, you have 3 different sources. You have, again, like we talked about before, you got individual differences. We're all different in our skill level, our attitudes, our past experiences. You also have participants may have been treated in different ways, right? So think about if you have a researcher who may be reading the passage to the person, right? They're reading the passage to the person, and just by the way that they read or the way that they talk to the participant may change the person's motivation, may change the person's attitudes about the experiment, right? Maybe they're more jovial to one person and more a little more meaner or mean to another person. And those 2 people experience 2 different vibes from the researcher. And that's going to influence maybe the scores on those exams. And then the last piece is the error of measurement, right? Which is inherent in any measurement tool, right? When I get on the scale, I may not get the same weight every time just because some scales may not be calibrated right, right? When we're looking at rulers, if I gave you a ruler and I wanted you to measure your dorm room or your room in your apartment, you're likely going to get, if I ask you to measure it in millimeters, right? You're likely going to get very different measurements each time you measure your room, just based on your measurement, right? Stopwatches, right? I asked you to time somebody, and that stopwatch is not going to be the same, right? So you think about for those who have run track before, somebody's running a 100, and you got coaches at the end of the finish line, and they all have stopwatches in their hands. You pull, everybody clicks the stopwatch when the person crosses the finish line, and then you check all the stopwatches. All those stopwatches are not going to be the same, right? Somebody got a quick trigger, somebody has a late trigger, and then somebody in there has hit it right on the money, right? And so those stopwatches, just based on the person who's holding them, may have some error in there. Okay, memory recall, personality inventory, all those things have error associated inherently in those tools. Okay, so that would be the random and the unsystematic error. Okay, so then what happens, right? When we calculate our between group variance, we calculate our within group variance, we calculate the total variance, then we have to create our ratio. And that ratio can be calculated only after you have your total variability, and then you break them into those 2 components. The numerator is the between group variance, okay? And that's looking at the variance between the means. Because again, when we look at um, the factors that contribute to that variance, you have the systematic treatment effects, as you can see here, and then you have the random and systematic differences. In the denominator, all you have is the random and the unsystematic differences. And again, that is associated and attributed to those individual differences. The researcher may have treated the participants very differently, and just the measurement tools have inherent error in them, okay? So in the denominator is oftentimes called the error term because that is essentially all the error for the variability, right, in the particular study. The numerator, again, that is where you start to see how the between group variance, and is there a significant difference between that between group variance, right? And so we're going to see that. We're going to see if the F ratio is at a particular number, then we can see if it's significant or not, okay? But again, you got the numerator, which includes systematic treatment effects and also the random and unsystematic differences, right? So essentially, this systematic treatment effects, right? That is going to be the difference. That's going to make the difference in our ratio, right? So without this, if this systematic treatment effects was 0, right? I got random and unsystematic differences over random and unsystematic differences. That would essentially be 1, okay? Because I have the same amount of variance or error term and the numerator and the denominator, right? But when I include the effects of the treatment, then I begin to see a difference in that number, okay? So again, the value that you obtain with the F ratio, again, is really determined based on the effects that exist, right? You have 2 possibilities. You have no systematic treatment effects at all, right? The differences are entirely caused just by random and unsystematic factors, right? And then the second piece is the treatment does have an effect, right? And it causes the systematic differences between the samples, right? So this will be the case of the first one, right? There's no systematic differences. There's 0, right? But say this number is a little higher, say it's 5, 6, or 7, right? Then you would see a treatment effect, and you'd see the F ratio go up in value. Okay, so we'll talk about when we're talking about computing our statistics and hypothesis testing. We'll do that in part 2 of this lecture. But when H null is true, right, the size of the treatment effect is near 0, right? So we go back. This is when the treatment effect or the null hypothesis is true, right? This is 0, okay? However, when the null and the alternative hypothesis is true, the size of the treatment effect is more than 0, and the F ratio is noticeably larger than 1, okay? And there are some systematic treatment effects, right? So if the null hypothesis is true, the closer the value for the F ratio will be to 1, okay? And that indicates that, again, differences between the treatment are just random and unsystematic, right? But when you start seeing a difference, you're going to start to see that the numerator is greater than the denominator. When that happens, then you'll start to get a larger F ratio. And that gives you a better indication that you may have some significant differences in your between groups, okay? Or between your groups, right? Okay? So here's a quick question, and then we'll wrap up after this, okay? It says, decide each of the following statements is true or false. Okay, so for the first one, it says, analysis of variance, or ANOVA, allows researchers to compare several treatment conditions without conducting several hypothesis tests. Okay, I'll let you pause that. And then the second one is, if the null hypothesis is true, the F ratio for an ANOVA is expected, on average, to have a value of 0. Okay, I'll let you pause it. But for those answers, the first one is true, right? The analysis of variance, it allows you to compare several conditions at one time, right? So you're only using one hypothesis test, and you're comparing several conditions simultaneously, okay? The second one is false, however, right? So when the null hypothesis is true, just like we learned in a couple slides ago, the F ratio will have a value near 1, right? Meaning that there is systematic treatment effect is a value of 0, but the unsystematic and the random error in the denominator and the numerator is about the same. So you should get something really, really close or near 1. Okay? All right, so we're going to stop there, and we're going to pick up on 12-3. We're going to learn about the notation. We're going to learn about the formulas, and then we're going to begin to compute an F ratio, okay? Following that, we will then talk about the post hoc test, and the post hoc tests are used when I have a significant difference because I want to know where those differences are, right? When we do find a significant differences in one-way ANOVA, all we see is, and all we know is that there is a significant difference, but we don't know where that difference is. And the post hoc tests allow us to determine where those differences lie between those sample means. Okay, so we're going to stop there. And on lecture 2, what we're going to do, we're going to work through the computation. We're going to talk about the notations because when we calculate a one-way analysis of variance, there are several things that we have to calculate. Because again, we have to calculate our total variability. We have to calculate the between subjects variability and the within subjects variability. And then we use those 3 things. We also have to calculate our degrees of freedom for within group, for between group, and then also for our total variability. And then once we get that, we talk about our mean square. Our mean square, we use our mean square then to produce our F ratio. Okay, and the F ratio provides us with the information that we need to either reject or fail to reject our null hypothesis. So again, until the next time, for part 2 of our lecture, I will see you all then. So I'll have a good one.